Yes, very good morning, one and all. So last class we started the properties of relations, right? Let's please respond, anyone.
Yes, sir.
Okay, the properties of thanks for your response. In properties of relations, we have total 6 properties are there. I think 4 to 5 properties we discussed in last class now. So first one is a reflexive relation. What it is in a reflexive relation? A relation R is said to be reflexive if A comma A is belongs to R. That simply we want to say A is related to A. That is we call it as an reflection. That is we call it a reflexive relation. Irreflexive relation. There is no relationship between itself. That is we call it an irreflexive relation. That means A is not related to A. 1 is not related to 1. 2 is not related to 2. That is we call it is an irreflexive relation. And coming to the third one is an symmetric relation. It is like a commutative property. Symmetric relation, which is like a commutative property. Okay, if A comma B, a relation R is said to be symmetric relation. Okay, if A is related to B, then B is related to A. That is we call it a symmetric relation. And coming to the next one is an asymmetric relation. Asymmetric relation. Asymmetric relation, it is an exact opposite to symmetric relation, not anti-symmetric. Please observe that, guys. Asymmetric, if a relation R is said to be asymmetric relation, then okay, if sorry, a relation R is said to be a symmetric relation. If A comma B, if A is related to B, then B is not related to A. I simply want to say it is an if A comma B is related to belongs to R, B comma A is not belongs to R. That is we call it a asymmetric relation. And coming to the anti-symmetric relation, most important one, anti-symmetric relation, guys. A relation R is said to be anti-symmetric on set A if A is related to B and B is related to A, then A equal to B, then A equal to B. And one more condition it is there. If you have A comma B, you can never B comma A unless and until A equal to B, unless and until A equal to B. That's most important one, guys. So that means here, for example, if I am taking this 1 2 3, if I am taking an example, it is an 1 second. If I am taking the relation, it is an 1 comma 2 comma 3, then a relation 1 comma 1, 1 comma 2, 1 comma 3, 2 comma 1, 2 comma 2, 2 comma 3, 3 comma 1, 3 comma 2, and 3 comma 3. Apart from that one is an sum of the combinations is accepted as a anti-symmetric relation. See, all diagonals 1 comma 1, 2 comma 2, 3 comma 3, all diagonals should be accepted as a anti-symmetric relation because it is an A equal to B kabatti. A relation R is said to be anti-symmetric on set A if whenever A is related to B and B is related to A, then A equal to B. 1 comma 1, 2 comma 2, 3 comma 3. Yes, we discussed in the last class. It is an anti-symmetric relation. Anti-symmetric relation. And one more combination. If you have A comma B, you can never have B comma A unless and until A equal to B. Unless and until A equal to B. That's why if we are having 1 comma 2, it is not must and should not be there 2 comma 1 only. 2 comma 1. For example, 2 comma 3, 3 comma 2 should not be there. Like that here. That's the type of relations only we are going to say it is an anti-symmetric relation. So that's why at last I mentioned here symmetric and anti-symmetric are not exactly opposites. Asymmetric is an exactly opposite, but anti-symmetric it's not an exactly opposites. That's the most important point, guys. Okay, next we are moving to the next concept. Yes, sir. This one is also we discussed, right? It's R4 and R5 are anti-symmetric. This one also we discuss. And next we are moving to the last but not least the property of the relation. It is an see everyone observe, guys. I think this will also be completed. Here, father, mother, and child. So 3 persons are there, and simply we want to say if A is related to B and B is related to C, then must should be A is related to C. That is proper. The type of properties we call it a transitive relation. Transitive relation. I repeat, A is related to B and B is related to C, and then A is related to C and down. So here, yeah, see, a relation R is said to be transitive if whenever if A comma B is belongs to R and B comma C is belongs to R, then A comma C is belongs to R, where A comma B comma C is belongs to A. So that type of properties only we can say it is a transfer relation sentiment. A simple example I given you, if a 1 comma 3, 3 comma 4 that is equal to 1 comma 4 ma. 1 comma 3, 3 comma 4 that is equal to 1 comma 4. Okay, see that here 1 comma 2, 2 comma 1, then simply we want to say it is an 1 comma 1. See another example, like if A comma B and B comma A, then A comma A. Another example. Okay, guys, please observe everyone. And A comma C, C comma B, then A comma B. Like, okay. And here, everyone please observe. Which of these is a transfer relation? A equal to 1 comma 2 comma 3 comma 4, R1, R2. Okay, and here a small modification, R1, R2, and R3, or transitive. Or transitive, because if A comma B and B comma C belongs to the relation, then A comma C is does also. Okay, and this statement is not required here. Okay, everyone please observe here, 1 comma 2, 2 comma 3 it is there, 1 comma 2, 2 comma 3 is there, then 1 comma 3 I mentioned here. And next coming to next one is in R2 equal to 1 comma 3 and 3 comma 2, and the simply I want to mention it is in 1 comma 2. And coming to the next one is in 1 comma 2, 2 comma 1, then simply I want to mention it is in 1 comma 1. It is a transitive relation. A relation R is said to be transitive if A is related to B, comma, B is related to C, then A is related to C and then A is related to C. So that type of property we call it as a transitive property. And so last finally I'm going to say is that the total, what is the relation? A binary relation. A binary relation. Okay, so that means must and should we have to maintain the relationship between two elements in it. Each and every relation have some properties are there. So the total 6 properties we have in that relation. One is an reflexive, symmetric, anti-symmetric, asymmetric. Next one is an transitive. So these are the different types of relation properties in. And now reflexive, symmetric, and transitive. If these 3 properties are satisfied, that type of relations we call it is an equivalence relation center. Equivalence relation center. And guys, and one more concept. If a relation R is said to be, if a relation R is said to be compatibility relation, a relation R is said to be compatible relation. One second, I want to mention here. A relation R is said to be compatible relation. Compatibility or compatible relation? Compatibility relation. Okay. Compatibility relation. If it is, if the relation is reflexive and symmetric. If the relation, a relation R is said to be compatibility relation if it is reflexive and symmetric relation. If it is reflexive and symmetric, first 2 properties if it is satisfied, that type of relations we call it an compatibility relations. Compatibility relations, guys. Okay, then we'll take one example. Guys. Okay. They're asking a question. Let A equal to 0, 1, 2, 3, 4. Show that R equal to 0, 0, 0, 4, 1, 1, 1, 3, 2, 2, 3, 1, 3, 3, 4, 0, and 4, 4 is an equivalence relation or not? They're asking this question now. Yes, sir. Tell me first of all. So we know if a relation R is said to be equivalence relation, it is must and should be satisfies 3 properties we know. That's one is an reflexive, one it is an reflexive, and second one is an symmetric, and third one is an transitive. In examinations, if they're asking this type of questions, First of all, I request everyone please mention what it is in a reflex, what it is in a symmetric, and what it is in a transitive. Then after, please start the solution for each and every point. Okay, for example, reflexive. Yes, we want to note it down something here, what it is in a reflexive and what it is an example. And then after, so we have to say it is an R is an reflexive, or it is an reflexive because of R is in a reflexive. Yes, because of, see that here. How can you say it is in a reflexive? That must should be 0, 0, 1, 1, 2, 2, 3, 3, and 4, 4 should be there. If it is not there, then we can say it is not in a reflexive. We need to check it out. 0, 0, yes, it is there. 1, 1, yes, it is there. 2, 2, yes, it is there. 3, 3, it is there. And 4, 4, it is there. So that's why we can say it is an R is in a reflexive relation because of like 0, 0, 0, 0, and next 1, 1, and next 2, 2, and next 3, 3, and next 4, 4. So already is there. So that's why we can say it is a reflexive relation. It is a reflexive relation. And next, we want to mention here a symmetric relation. A relation R is said to be symmetric if A is related to B, then B is related to A. That type of relations we call it as a symmetric relation. We need to mention the definition in examinations. Don't solve directly. Okay, is it symmetric or not?
Symmetric.
Yes, it is a symmetric relation because we have 0, 4, it is there. Of course, 1, 1, 2, 2, 3, 3, 4, 4 also we call it symmetric, but others also is there. That's why we want to focus on that first of all. 0, 4, 4, 0 are there. Yes, 4, 0 it is there. 1, 3. So 3, 1. Yes, it is there. 3, 1. So simply we want to say it is an R is an symmetric relation. R is an symmetric relation. R is a symmetric relation. Okay, because of we need to mention why it is an symmetric relation also. So why it is an symmetric relation? Here we have some 0, 4 it is there, and 4, 0 it is there, 4, 0 it is there, and next 1, 3 it is there, and then after 3, 1 it is there. 3, 1 it is there. Okay, next, R is an transitive or not? We need to find out transitive relation or not. Okay, because of, we need to say like that here. For example, yes, we need to take one combination like 0, 4. Everyone please observe 4, 0, 4, and next one is in 4, 4 it is there. So that means what?
0,
One second, sorry. Yes, simply I want to mention like this here. 0, 4, 4, 0 is there.
0, 0.
0, 0 it is there. Yes, this is one combination we want to take like that. All combinations are there here in this example. For example, 1, 3. For example, 1, 3 is there, and 3, 1 is there, and 3, 1 is there. Sorry, 3, 1 is there, and finally we are getting 1, 1. Like lots are there, but actually we need to mention one or two, no issues. So simply we want to say it is an RSN transitive. So because of 0, 4, 4, 0, 0, 0 it is there. Yes, a very good 508, 1, 3 and 3, 1. Simply I want to mention it is an 1, 1 and 1, 1. So simply this is the way we want to solve whatever the relations is an equivalence relations. Okay, but in examinations we need to mention the definitions of each and everything. We need to mention what is the reflexive relation and what is a symmetric relation and what it is in a transitive relation also. So then after we want to solve each and everything, then we need to show it is an equivalence relation or not. Equivalence relation or not. So guys, any doubt here? Then we'll take another example otherwise. Yes. Shall we take another example or not? Yes, a clear, very good answer. So, okay. So only one student mentioned, that's why I want to take another example more. Let x equal to, let x equal to 1 comma 2 comma 3 comma 4 comma 5 comma 6 comma 7 ma. Okay, and the relation r equal to, and the relation r equal to x comma y, and the relation r equal to x comma y, such that where it is x minus y, such that x minus y is divisible by 3, is divisible by 3. Show that R is an equivalence relation. So this is the question they asked me. Yes, please. Guys, tell me. First of all, what is a relation? Guys, please respond. So this is the way to we want to solve. Excuse me. This is the way. This is the way to we want to solve all types of relations in term. Equivalence relation. A relation R is said to be reflexive, symmetric, and transitive. Then that relation we call it as a equivalence relation. Sometimes they are giving different examples now. So I request everyone please check it out here. Let R denote a relation. Let R denote a relation on the set of all ordered pairs, on the set of all ordered pairs, in the set of all ordered pairs of positive integers, of positive integers, let it be defined as x comma y, as x comma y related to u comma v, related to u comma v, if and only if xv equal to yu, show that R is an, show that R is an equivalence relation. Show that R is an equivalence relation. Guys, everyone please observe. So till now actually we are getting some set of integers. Let a equal to 0 comma, let a equal to 0 comma 1 comma 2 comma 3 comma 4, and something they're giving like a 0 comma 0. Otherwise they're asking like r equal to x comma y, says that x minus y divisible by 3, show that R is an equivalence relation. But in this example they're asking differently. Okay, let R denote a relation on the set of all ordered pairs of positive integers. Let it be defined as x comma y is related to u comma v if and only if xv equivalent to yu. Show that R is an equivalence relation. Show that R is an equivalence relation. First of all, if I want to solve this type of examples, first of all, we have to know what are the three properties satisfied, then that relation we call it the equivalence relation. First of all, we want to know. So already we know one is a reflexive, and second one is a symmetric, and third one is a transitive relation. Yes, we know that is an. Yes, first of all, we want to take a reflexive relation. Reflexive relation. Yes, so we know what it is in a reflexive relation, guys, right? Reflexive relation already we know. How can we prove this one is a reflexive relation? Simply we want to say this one is an, okay, if I'm taking for example x comma y is related to x comma y is related to x comma y. So this is a reflexive relation. As per the definition, we want to say x is related to y and related to x equal to y and term. So this is a reflexive relation. Okay, now if it is unlike, as per the definition, if x comma y is related to x comma y, then that is an equivalent to, how can we define this one is an, as per the definition? See that here they define here xv uy. That means we want to take it as an xy equal to yx, xy equal to yx. That means if I am applying like here xy equal to xy, right? Xy equal to xy. So just I want to mention like for your understanding like this here. Just I applied here yx is a commutative law I applied here, a into b equivalent to b into a, both are same. So I applied like that here xy equal to xy. So simply we want to see it as a reflexive relation. Xy is related to xy and term. And next one is an, what is the next one here? So x comma y is related to u comma v. One second. Yes. Uh, yes, a very good mark. Hence it is a symmetric. Then we want to prove it. We'll take an example like, see, if I'm taking for example, x comma y is related to u comma v. Okay. Yes. If x comma y is related to u comma v, then already we know how to define, right? We know how to define. They're given some equation, xy equal to yu, xy equal to yu. One second. Yes, sorry for the interruption, guys. Yes, xy equal to yu, they define, they given, right? Xy equal to yu. Okay, now what is the what is a symmetric, guys? A symmetric means uv related to x comma y, right? Uv is related to x comma y. Can we write like this here, guys? Yu equal to xv. Yu equal to xv. Can we write like this? And then after, okay, and I want to write down here uy equal to vx. Can we write like this here, guys? Okay, as per the definition, see that here, everyone please observe, u comma v is related to x comma y x comma y. See that here, everyone observe, as per the definition how they given here, x V, XV, one second. Okay, XV and UY or YU, XV, YU. And see that here, so A related to B related to A, that is we want to prove. A related to B and B related to A, that is we want to prove. Okay, guys, XV, YU, as per the definition they given here. So A equal to B, that's I am taking here B equal to A, B equal to A. And here YU is there, and by using commutative law, A into B, B into A, both are same by using commutative law. That's why I mentioned here U into Y, that is equal to V into X. So as per the definition, can we write like this here? See here, it is an UY, VX, like YU. So this is the way to we want to prove it is a symmetric quantum. Hence it is a symmetric. Hence it is a symmetric. And coming to the third one, and we want to prove it is in a transitive relation. Transitive relation. So here they given only they given only two concepts. X is related to Y. Sorry, X comma Y is related to, okay, X comma Y is related to U comma V, and I want to take it as another example. Okay, that is U comma V, that is U comma V related to some example. Let I have taken this one as an like let, okay, let X comma Y is related to U comma V, okay, and U comma V is related to something. I want to take it as an M comma N, M comma N. Finally we want to get guys, A is related to B, B is related to C. Finally what we got, what we want to get?
X comma Y related to M comma N.
Very good. X comma Y is related to M comma N. Okay, then that is we want to prove that we can say it is a transitive relation term. Okay, first of all we want to take it as an X comma Y is related to U comma V. So as per the definition they given something here, that is equal to X comma V equal to Y comma U, right? They given already, they given X Y X sorry XV YU, they given like this one is an, okay. And same I want to mention, like as per the definition also we want to mention this one is an, yes, UN, I want to make a gap, UN, that is equal to guys please, as per the definition,
MB.
MV or VM, whatever it is you can take, VM, okay. And finally, okay, okay, okay. If I'm taking for example in this one, everyone please observe, xv equal to yu, xv equal to yu. If I'm taking for example both sides multiplying with, for example, m, both sides I'm multiplying with mm. Okay, if I'm going to applying this one is like, sorry, okay, that is an x v m, right? That is equivalent to y u m, y u m. Both sides I'm applying here. I'm multiplying with the both sides M. Okay, now tell me here, if I'm taking for example Vm, which is an equivalent to, they given already Vm equal to Un. So here I want to take it as an X U M. Okay, is it okay, guys? Guys, is it okay?
Okay, sir. It's clear.
Just I'm going to replace with whatever it is in Vm. Already we have some Vm equal to Un. That's why I want to change it as an Un. Okay, and next one is in Y U M. Okay, so both sides I'm going to cancel both sides. I'm cancelling U. So both sides I cancel U. If I cancel both sides U, what happened here? Xn, that is equivalent to
YM.
by M. Okay. Yes. So tell me guys here, how can we make these changes like here? X comma Y is related to M comma N. Is it okay? Guys, is it okay?
Sir, it's okay.
Yes. See that here. Xn equivalent to Xn equivalent to Ym. So is it possible to write it down like this here? X5 comma X comma Y relation M comma Nn. So finally we are getting like here, A is related to B is related to C, and then finally we are getting A related to Cm, A related to C. So finally it is an hence it is a transitive, hence it is a transitive relation. Therefore a relation R, therefore a relation R is equivalence relation. So this is the way we want to prove if they're asking the question like this one is one. Let R denote a relation on the set of all ordered pairs of positive integers. Let it be defined as x comma y is related to u comma v if and only if xp equivalent to yu. Show that R is an equivalence relation. Show that R is an equivalence relation. So simply we want to mention a reflexive means simply I want to take it as an x comma y is related to x comma y. X comma y is related to x comma y. As per the definition xy yx. So yx I want to make it a changes as per the commutative law is also x comma y. So xy. The finally xy equal to xy. Xy equal to xy. So simply hence it is an R, hence R is an reflexive relation. And then after we want to prove it is an symmetric relation. That means x comma y is related to u comma v. We want to show that u comma v is related to x comma y. So this is the way to we want to take it, guys. Hence simply we want to make it as a symmetric. And transitive, just I applied both sides. I'm multiplying with m. If I am multiplied with m, x v m equal to y u m. So already we have some equality, v m equal to u n ani. So that's why I mentioned here x u n equivalent to y u m. So here both sides u is there. That's why both sides I cancel u. So if once I cancel u value, x n equal to y m, x n equal to y m. So okay, this concept I want to write down like this here, x comma y is related to m comma n ani. Hence it is a transitive relation. Finally, therefore a relation R is equivalence relation at all.